All right, thank you for that. Anyway, so why don't we get started? Where we left off, oh yes, so we have an assignment due, project one, due this evening at the usual 1 second before midnight. Please make sure you're not waiting until the last minute to hand that in. It is based not on network time, which allegedly the network is supposed to be synchronized with the network time server, but the time is marked by what telephone time, namely the time for the server. There's some clock skew as it pertains to the synchronization for the clock on your device attached to the network. So please rely on the time that would be on your cell phone or watch or what have you. Okay, so where we last left off, we talked about visualization, and we left off with bar chart, particularly the version of the bar chart that was transformed to depict relative frequency. And as we had discussed, the bar chart describes the counts of the number of data items that have some particular property, label, or value. And so in this example, along the horizontal axis for this bar chart, it has the seasons of the year ordered in spring, summer, fall, and winter. Because these are categorical, they don't have to be in that particular order. You could decide to sort them in some notional temporal order, but remember, for things like the semester for school, you would say fall then spring instead of spring then fall. And so these are categorical, but you need some ordering, and they just chose in this example to order it as spring, summer, fall, winter, which coincides with the seasons in the calendar year, but it's not required to order them left to right in that order. So nonetheless, along the horizontal axis, we have the seasons of the year, and along the vertical axis, we have the relative frequency, and this chart corresponds to the seasons in which children were born for a particular family. And so they took the plain vanilla bar chart, which traffics in counts along the vertical axis, and they divided the number of counts for each one of these categories, spring, summer, fall, and winter, by the total number of items that were depicted in the original bar chart. And in doing so, you convert from frequency to relative frequency, where that relative uh, connotes the fact that you're dealing with percentages or proportions. And as such, you can think of this also as a probability distribution. It's absolutely the distribution of children as it pertains to the seasons for the year. And so, again, we had a count of one. One child was born in the spring, and you divide by five, that's 1/5, or 0.2, or 20%, or 20% probability if you want to treat it as a probability. So that's where we left off last time. Any questions about this? Okay. So let's continue on and let's go through a couple other types of visualizations. And this might be very mundane for some of you, but it's certainly a requirement visualization for a course like this. And so this is a pie chart. And a pie chart is called a pie chart because it looks like a pie from top view, the pastry. I guess you call it a pastry. No, pie's not a pastry. What is a pie? Cake? No, like a pastry, but you know what a pie is. It like usually has fruit and it's baked and sugary and stuff like that. But nonetheless, it looks like a pie from top view, and each of these wedges, sliced, if you will, or into which the pie is carved, represents a percentage. And so this percentage is relative to the entire area of the pie. And so each one of these slices is typically labeled with some label, and that label represents a value. And you can kind of see a correspondence between the pie chart and this relative frequency version of the bar chart from the previous two slides ago. And it does represent relative frequency, but it does it in this different geometry. And so, most modern spreadsheets can create pie charts. Matlab also has APIs, and I'll show the API names and leave it to you to look them up and tinker with them yourselves for doing these types of visualizations. So in this particular example, you have a total of 24 hours representing a day, and this pie chart corresponds to average time usage on a weekday day for college students in I believe it's the U.S. And so for example, 8.7 hours for sleeping is carved out of those 24 hours. And if you look at that, well, that's just over 1/3 of the number of hours in the day. Theoretically, people sleep 8.7 hours a day on average. And if you can see the area of this shaded blue region corresponding to the sleeping activity, it's a little bit over 1/3 of the total area of the pie. So you can imagine this, if you were to kind of repeat this and kind of replicate it here and replicate it here, it would cover just a little bit over the total area of the pie. Okay, all right. Any questions about this? Does that make sense? And so, particularly when you have an experiment, one of the first things you should do, as I'd said, I think on Thursday, um, that you look at your data, and the purpose of a visualization is to help inform the choices for the analyses that you're going to perform on the data. And the quote unquote right visualization will very clearly highlight what it is about the data you should enterprise to pursue with your statistics and other calculations. Okay, so let's go on to scatter plot. A scatter plot can be in 2 dimensions or in 3 dimensions, and in this particular case, it's 2 dimensions. You can't draw a scatter plot in more than 3 dimensions because you can't visualize it on a 2D surface of a board or a piece of paper, not easily. And so in this particular case, we have a Cartesian plane in 2 dimensions. We have the first axis, x, the horizontal axis, going off to plus and minus infinity. And then we have the vertical axis, y, going off into plus and minus infinity. And so here, this x and y, these axes, represent variables, and each of the tick marks along these axes represent values that these variables can take on. And so if you're going to measure 2 different quantities, one will designate as x and the other will designate as y, you can actually plot these observations of 2 things as coordinates registered in this Cartesian plane. Right, so here we have 2 values, and let's call, or 3 values. The first measurement for its x value you measure to 0, and the second measurement for its y value you measure to 0. So we would depict those 2 measurements as a dot whose coordinate is 0, 0. Likewise, let's see, say, for example, for the sake of consideration, if our second measurement you measure -2 for x and a -1 for y, you would register or visualize those 2 measurements for your second set of measurements as a dot at coordinate -2, -1, right? And likewise for that third point. Okay, so each axis encodes a variable's value, and you can imagine if you wanted to visualize 3 variables, then you would plot things in 3 dimensions. Okay, and so what the scatter plot gives you is a visual understanding or visual depiction of the relationship between 2 variables, because depending on the shape of the cloud of points, as it were, in the scatter plot, you can visually depict a lot of types of relationships between the measured variables. Okay, so this is an example of a scatter plot, and this particular scatter plot looks at the ranking of a college football team. You can imagine Division One, and the head coach's salary. And so along the horizontal axis, we have head coach salary measured in millions of dollars. So it starts at 0, and it can go upwards of 8 million in this particular graph, and that's annual salary. And along the vertical axis, you have the rank of a college football team. And so in this particular example, in terms of the vertical axis, lower means better, right? Now, to me, that's a sort of unfortunate way of depicting it, but it's really, really important when you describe a visualization and when you interpret or read a visualization that you understand what the axes mean. In most examples, right, it's sort of natural for humans who look at a lot of visualizations that this idea of bigger means better, right? And so in this particular case, the better team is the one ranked closer to 1 or closer to 0, right? The one that is worse is the one that's further away from the ranking of 0. So in this particular case, higher up, or bigger, if you want to call it that in the graph, means that you're a worse team, okay? So if we take a look at one of these points in the scatter plot, every time a point, say a point over here to the right, so if you leave, class policy says that you can't come back. Sure. Okay. So if you cast your gaze to some of these points here. As you go to the right, your call it the annual salary of the coach gets bigger, right? And the general trend you'll notice is that as you go to the right, the salary gets bigger, but also the vertical value, the y-axis, the height of the point, if you will, gets smaller and smaller. So what does that mean? Well, without necessarily looking at the particular college football team, right? You can visually look at this and you'll notice that there's this trend that as you go to the right, you also go down. It's sort of a downward sloping point cloud. You can imagine this thing as being sort of oblong shaped and it's oriented so that it slopes downward. And so what that means in terms of trend is that the better teams or the teams more highly ranked or their rank is closer to one pay their coaches much higher salary. Now, the reason for that could be manyfold. Maybe if a team is a stronger team, they're a more winning team, and a more winning team is a more moneyed team, and therefore they can afford to pay a college coach more salary or higher salary. Or it could be that because the coach has a higher salary, they can afford a coach maybe with certain specialized experience or certain other training that is more effective in getting better performance out of a team, right? So there are lots of reasons why, but the key takeaway here is that from our plain vanilla scatter plot, just by registering these points graphically in 2 dimensions as points in a coordinate system, you can see the relationship and the general trend as to what happens if you increase or decrease values in one of these 2 measurements corresponding to the horizontal axis, annual salary, or the vertical axis, which is the rank. Okay? All right, any questions about that? Make sense? So it's really important to choose your variables, and sometimes you might have more than 2 or 3 variables to measure, and you want to depict them as a scatter plot. And the practice is typically to choose 2 or 3 of those k many variables. So let's say you had some study or some analytical problem that you were tasked with solving or depicting. You might have 10 measurements. You choose 2. Right, so maybe it's different things about the student experience at DSU, and maybe one of them is years to graduation, and the other is, the number of dollars in student loans, right? And maybe you have 8 other measurements. So if you wanted to depict this, you can't plot 10 measurements, but you can certainly plot 2 or 3 of them at a time and try to get an understanding, in this case, of what the relationship is between pairs or triples of these variables that you've measured among the 10. Okay? All right, any questions about this? All right, so again, scatter plot is one example, and this allows you to look at the relationship, the coupling, if you will, between measured variables. And so there's something called a trend line, and this is more formally called the regression line, right? And what the trend line does, imagine if you were to take all the average x values, horizontal axis values, and all the average y values, and you were to plot the result of that. So you took all the salaries for each one of these measurements, and you took all of the ranks. You can depict these as a linear relationship, and that's exactly what this trend line does. And so the beauty of the trend line says is what is the general relationship, in this particular case, the linear relationship between the coach salary and the ranking of the team. Now, is it completely descriptive of every single example? Absolutely not, but it does good enough and does fairly, does okay, good enough for typical values as far as head coach salary is, and certainly gives you a functional relationship between the two. So now, once you fit a trend line or perform a regression in this particular example, you now have in functional form y equals mx plus b, a mathematical equation that describes the relationship. So what could you do with something like this? Suppose you were a college administrator, or suppose you were a recruit for some, athletic activity or what have you, and you wanted to know how much you should pay the coach, right? Or you wanted to know, all sorts of measures. You would take a lot of data, you would fit the trend line or perform a regression analysis to get this linear relationship, and then you'd use the formula describing this line to now give you values based on analyses. So that gives you the ability to kind of play these what-if scenarios. What if I paid a coach, 5% more? Is that going to have an impact based on this data? Is that going to have an impact on how the team's ranking might play out next season? Okay. Now you can imagine in this example, This talks about college coach salaries and rank, but you could imagine couplings for all sorts of things. Maybe it's dollars in financial aid and years to graduation. And you could argue that, gosh, well, if a student had more funding, he or she perhaps wouldn't have to take part-time employment, and that would tend to speed up or reduce the number of years to graduation, right? So you can do all sorts of analysis. It's just an example that I found online I thought was very illustrative, pertains to this particular example. Okay. Any questions about this? Okay. So that's a scatter plot. Let's take a look at a line chart. So a line chart kind of looks like a scatter plot, but it's a little bit different. Here we have a line chart. Let's look up top, and both of these charts, it's the same chart, but one is connected line chart, and one just uses the points akin to a scatter plot. This relates to the share price for one share of Apple stock on the open market. Along the horizontal axis, we have trading days, right? And these are marked in temporal order along the horizontal axis. So we have March 2nd each month, April 2015, May, June, July, August, September, and so forth. So, and on the vertical axis, we have the stock price in US dollars. And so you can see for this particular example, for 2nd of March 2015, the share price was about 128, 129 and change for Apple stock. And you can take this scatter version of this line chart, and you can connect subsequent points going from further longer ago in time to more recent, going from your left to right in this plot. And this gives you a line that describes the performance of this security. Now, of course, you'll notice that in general, it kind of looks like it's, well, it kind of, goes up and down for shorter amounts of time. For this particular period of time that's depicted, the general trend is that it's going to go down, right? So just like the other scatter plot that we talked about, you can also draw a trend line for these stocks. Okay. Any questions about this? So this is an example of a trend line, a regression line, and it describes a linear relationship. And this linear relationship covers a larger period of time than what is depicted using the raw line chart. And so why do people use this? Well, there are all sorts of things which are beyond the scope of this class that people use to try to predict or help inform their choices about what they believe a stock is going to do over time. Now, granted, you use the actual data, but you also use market news, like from, say, Reuters or Reuters feed, right? So, for example, if some event occurs and maybe there's a lot less availability of silicon used to produce computer chips. That makes computer chips more expensive, and that's going to ultimately affect the share price because the cost of the components influence the cost of the finished product. And so in absence of Reuters feeds and other news feeds related to a company and its supply chain, you could certainly say, okay, well, I know that in a 6-month period of time, based on this chart, it's going to go down. So the question then you'd ask yourself is what happened, bless you, what happened during that time? Right? You're trying to take the gross level behavior or the long-term behavior, and then, certainly you can subscribe to a Reuters feed and go back in time with the Reuters feed, say what events happened in society or around the world that might have influenced this particular behavior in the share price. So then what you could do with that is then try to predict what's going to happen maybe 3 months or 6 months ahead of time, and use that to your advantage to try to maximize profits that you're trying to make if you're trading or hedging or things like that. Okay, all right. Any questions about this? Now, of course, in the real world, they use something or modifications of something called the Black-Scholes model. They use differential equations, so they're using derivatives based on a number of factors, and also this notion of momentum. Things don't abruptly change in value. They kind of go indirectly through values in between two endpoints. And so you could actually make a whole living and career off of modifications to Black-Scholes. If you've ever looked at the jobs on the job boards, there's something called a quantitative modeler. and they do exactly that. They look at all of these different models using derivatives, as in the calculus derivative, in time on these sort of charts to try to come up with more efficient or efficacious, more correct models of what the behavior of a share price might be, in addition to what the influences on a share price might be. Right? There's a whole umpteen many $billion uh, discipline in that. Okay. Any questions about this? Make sense? So not only do we have the scatter points, we also have the lines connecting them to give you some notion of behavior over time. And like the other scatter plots that we talked about, or scatter charts, you can also draw the trend line, and you can actually solve for that trend line using something called a regression analysis. Okay. So another benefit of a line chart is that it allows you to make easy comparisons between similar systems. And this is a great example for that. This represents temperature over the course of some period of time for a number of different locations. And so here along the horizontal axis, we have the month, and these are sorted in chronological order from January to December, but they didn't have to be, right? And on the vertical axis, we have temperature measured in degrees Fahrenheit. And so we have three plots here. These are line charts. We have the scatter points, the squares, the circles, and the triangles. So the squares are in green, the circles are in blue, and the triangles are in red. We also have the lines connecting those scatter points to form a line chart in time. And so the green represents Asuncion, Paraguay, city in Paraguay. The blue chart represents Pueblo in Colorado, USA. And the red represents Jianshui in China, right? So we have three different cities, and they're at some geography, and someone has measured the temperature over time for these three different locations. Now, one of the things that's really apparent is that you'll notice that for Pueblo and Jianshui, you'll notice that while Pueblo and Tianshui, they're not exactly the same, but they exhibit very similar behavior, right? They kind of look like this bell curve. They start low, and then they come up. They turn the corner right around the middle of the year in June, and then they come back down, right? So they exhibit very similar properties in terms of temperature. But if we look at Asuncion, Paraguay, which is south of the equator, right? You'll notice it's kind of the opposite. It's this parabolic or this bell curve shape, but it's turned upside down, right? So it starts high in January, so it's summer there in Asuncion, and then in the middle of the year, at the peak of our summer, it's the coldest there, and it's still a relatively humid or relatively temperate area, so it doesn't get very cold like how Florida doesn't get very cold. And then towards December, it gets hot again, right? So why would somebody use something like this? Suppose you're in the winery region in France, and you want to grow grapes somewhere else, maybe to have, as a supply chain, to have year-round production, right? So grapes don't grow in the wintertime, and you want to locate some other geography that exhibits similar habitable temperatures suitable for growing the particular type of grape you're interested in. So you take this chart for a bunch of cities or a bunch of regions throughout the world, and then you pick one that has similar temperature properties. Now, it's not just temperature for growing. You're also concerned about precipitation. You're concerned about soil quality and soil content and stuff like that. But what this chart does give you, and that's the point I'm illustrating here, is that it allows you very quickly to make easy comparisons between two different systems, the temperature of these different cities, to try to find similar or dissimilar types of behavior. Okay, so for example, if you were going to choose an area to grow grapes that's similar, you'd have a bunch of these measurements. You'd look at the graphs and you say, aha, well, Pueblo and Tianshui are very similar. Now let me further investigate things like soil and precipitation. Okay, and you can automate these sort of comparisons. But in the least, visually, it allows you to make very quick comparisons to further direct any analyses. Okay, any questions about this? No? All right. So Matlab. Now, Matlab isn't the only thing that can do this. Spreadsheets do it quite easily. In a spreadsheet, you have a data range on the waffle, as it's called, the data area. You highlight it, you select a graph type, and then it plots the chart. You can update the data, and it updates the chart. These are some of the APIs in Matlab. You can depict categorical variables as cell array. Of course, histogram is a bar chart, and you can tinker with the settings on that bar chart, bless you, the number of bins and all sorts of other measures. It can give you the raw bin counts. You can also normalize those bin counts and produce a relative frequency chart. Pi is the command in Matlab for pie chart, at least as of Matlab, I think it was 2018. I don't think it has changed in 2019. It has scatter plots, and it has scatter plus plot, which is the line chart. It takes the scatter points and connects them with a line. Okay. All right. So please do tinker with that. Matlab is required for the course. And in absence of having a spreadsheet, access to a spreadsheet, I encourage you to use Matlab for your visualizations. We will have an assignment where you will be doing survey design and visualization. Okay. All right. Any questions about this? Make sense? Okay. So we'll end with that module. Let's please make sure you're keeping up with the reading, and don't wait till the last minute to submit your assignments that are due tonight. All right. So let's pull up the next module. And in this next module, we'll talk primarily, among other things, about experimental design. So again, there are the data points about the assignment due tonight. Please make sure you're also keeping up with the reading. So there are lots of populations, and there are lots of reasons why people study groups of entities. For example, bees. Bees are responsible for pollination, right? So we would not have any vegetables, any fruits, any of that stuff without bees, right? In fact, if you've ever been to what's it called, Pfeiffer Orchards here in Camden, Wyoming, Delaware, every spring, early in the spring, they rent bee boxes, and they set up these mobile hives, and they have a partnership with bee farmers. I forgot what the name for bee farmer is. Can't remember the name. Anyways, so they have a partnership with some bee farmers, and they rent some mobile hives. They bring the hives, they set them up among the fields, and the bees do their wonderful job pollinating all of the blossoms, which eventually turn into things like peaches and apples and all sorts of fruits and vegetables. So people study bees. They're very important ecologically, because without bees, we wouldn't have fruits and many vegetables. This bottom frame, that's rush hour traffic in Boston, near downtown Boston. And of course, when you have large groups of things, congestion happens on the highway, and people are always enterprising solutions to try to fix this congestion, because that results in a huge loss of productivity. It can take you hour and a half, 2 hours to go 3 miles. It's unbelievable. But nonetheless, solving these sort of issues requires you to get information from a large group of people. Now, of course, when you produce a visualization, not only should it be compelling to capture people's attention, it should also depict the type of information you're trying to generate. Now, I went off and I found these two visualizations because they look really nice, right? It really is visually pleasing, and it's also very interesting, and you could certainly use this to depict something about any problem. Consequently, the graph on the right is something about GDP, gross domestic product, which is the total value across an area of economic output. If you look at all of the goods and services people produce in an area, put a dollar value on that, add it, that's called GDP, gross domestic product. And that's a measure of economic vitality, if you will, of an area. And then the other one just deals with population. It just looks nice. So this is just to drive home the point that, of course, if you're going to study a large group, it's really important to have a good visualization that very obviously illustrates the point that you're trying to make. Okay? So let's take a look at populations. And so last semester, you learned about distributions, and we said a distribution describes the values of data that occur, right? You can almost think of a distribution as a law that governs the values that you see for some sort of measurement. And so we talked about and studied a lot of different distributions in stochastic computing, and each one had certain assumptions. So for example, the geometric, we said you have a bunch of yes-no trials, but all of the K trials in the beginning had to be no's, and they ended in a single yes, right? And so this is the Poisson, and the Poisson, its mass function is lambda to the x power e to the minus lambda upon x factorial, and the Poisson dealt with occurrences of events that are in time. And we use this word module of observation or window of observation to describe the average number of events that occur in time. And if we were to plot the mass function for Poisson, this lambda parameter for the Poisson kind of changes the skewness of the Poisson distribution. And then we did something like we sampled from it. We simulated it, whether it was through simple stick breaking or using some of the sampling routines from Matlab, and we were able to use those samples in problems and answer questions about different systems that we're trying to mimic. Okay, well, it's not always clear when you talk about a distribution. A distribution, in essence, as we studied last semester, is an educated guess about how you believe the data occurs, right? You're trying to choose one based on what your understanding of a problem is, and then you're trying to put them together in a way that mimics the system that you're trying to study. So for example, the lemonade stand problem, in that problem, we said you have a certain rate of customers that arrive at the lemonade stand for the first hour and then at the second hour. So one of the questions that you might ask, well, is modeling that problem on an hour-to-hour basis the right approach? Maybe it should be for every 15 minutes or every 5 minutes. Now, of course, from a practical standpoint, when you make those sort of decisions, the model design, you have to trade off this idea of granularity, how fine scale your model is, and computation. Because the more fine scale you model a problem, say down to every minute or every second, the more distributions you need to sample from, the more moving parts your model has, and you pay for that with increased computation. So in general, it's not always so clear how the data's values arise, and that gets even more damning as you're dealing with very large, complex systems with a lot of interrelated, interconnected parts. And so some distributions govern the observable data's values, but sometimes you have no clue about what that distribution could be. So in essence, you have floating out there all the possible values that a random variable or measurement can take on, right? And there's this invisible thing called a distribution, and it's feeding you values, but you don't know 100% what it is. It's not always clear. So we carried this example of the homeless population, and now I'm going to introduce a little bit more formal terminology. This idea of a population is defined as the collection of all of the possible units of interest. So for example, if we're talking about bees, right, we talk about all the different species of bees that are out there. That is our quote unquote population, right? And so governing this, when we gave the example for the homeless, we made a simplifying assumption for the sake of talking about homeless population. And in that discussion, we said there were 4 subgroups that make up the homeless population. Those 4 subgroups were the homeless veterans, the homeless families, those struggling with drug addiction, and the aged out foster kids, those who've aged out of the foster care system. Now, of course, we made a simplifying assumption that these 4 different categories or subgroups of the homeless population, a so-called hierarchical population, do not mix with one another, right? We said that these are unique categories, and someone who is a homeless family is not also a homeless veteran, right? That's not true in the real world. And of course, if you want to add more realism to it, that model gets more complicated, and you pay for that complexity with increased computational need. So nonetheless, we talked about these 4 groups: the veterans, the families, drug addiction, and foster kids. And let's suppose that for the homeless population, there's some proportion that exists. You have some number of homeless, and some percentage of them are veterans, some percentage are families, some percentage of are drug addicted, and some percentage are foster kids. So let me ask you, do you know what those percentages are in Delaware, for all of Delaware? No? Do you know what it is? All right, let me make it easier. How about for Kent County? No? Let me make it even easier. How about Dover, right? Only 37,000 people in Dover. No, you don't know. I don't know what it is. And this is very illustrative of sometimes what happens in the real world is that you have no clue what the ground truth numbers are for your system, right? And this is indicative of what happens in large scale, real world types of analyses. And so for these examples, or for this example, let's just make this assumption, right? I just made these numbers up. I don't know what they really are, but let's just assume 20% of the homeless population are veterans, 15% are families, 30% are drug addicted, and the remaining 35% are foster kids. Hopefully this adds up to 100%. That's 30, 65, 75, 8. Yes, that's 100%. Okay, so let's just make that assumption, right? I'm not claiming to know, just made these numbers up for the sake of example, okay? And so these numbers that govern some characteristic in your population, those are called parameters, right? And sometimes in the literature, you read the phrase the governing parameters, or you'll say this is governed by a distribution indexed by the following parameters. And a parameter is formally defined as a numerical characteristic of a population, right? So in this particular case, the numerical characteristic or the parameter is the proportion of your population as a percentage that falls into one of these categories, okay? So we have a population, a collection of all possible units of interest, and we have the parameter, numerical characteristics of a population. Now, when we talked about the Poisson distribution, we said lambda is the governing parameter. That parameter tells you about the values generated by or governed by this Poisson distribution. That is a numerical characteristic of the population of values describing the number of occurrences that you can observe in time, right? So it is exactly the same type of parameter. We have some invisible, unseen distribution generating the values you see, and that distribution is controlled by these parameters. Okay. Any questions about this? Does that make sense? Yeah? Okay. So what did we do? Well, we know the parameters exist, but we have no idea what these ground truth parameters are, what the actual ones are for the population. And so we observed units from the population. When you observe units from the population, that's called sampling. You're taking from the population, making an observation or taking a measurement, right? So parameters do exist, but you don't know what they are, these parameters that govern all of the values from the population, right? So you sample. You pull some member of that population that you have access to, and you observe or measure something, and that's called sampling. So what did we do in that example? We pulled someone who was a veteran. We pulled someone who was homeless family, likewise for drug addicted and foster aged out foster child, and we asked him or her some questions. Okay? All right. So the hope then is that if you've done this well enough, that the sample that you have, the folks for whom you know some information, you can make those measurements, that they're representative of the entire population. Now, this is what it really looks like without those line draws that separate the population into subgroups, right? I just did that because it looks nice on the board for explaining the concept. But in truth, you really don't know who is a homeless veteran, who's a family, who's drug addicted, who's foster kid, until you actually sample someone and ask him or her. You can't go out beforehand and say, I'm going to sample a homeless veteran. I'm going to sample an aged out foster child. That doesn't happen in the real world, right? So you go out and you sample, and this idea, well enough, if you've done it well enough, you hope that the sample is a good enough representation of what's going on in that population. Okay, so you observe a sample, and now you make statements about a population by computing functions on the sample, right? So you have some representatives of the larger group. You perform some function on that data you collect from those representatives, and then those functions are called statistics, right? A statistic formally is defined as any function computed on a sample, where the sample is a representative of the population. Okay? All right. Any questions about this? Make sense? So this is still just a definition. So let's say you sample 1,000 members of the homeless population, And we're going to depict that sample of 1,000 people to be big X. That's our set. And that set consists of the first person you sample, meaning you find someone and you ask him or her questions. Let's call that X1. Then there's an X2, little X2, little X3, little X4, and so forth, up through and including a little X1000. So you sample 1,000 members of the homeless population. Well, then you take that sample and you measure some function. So that function could be, what's the number of people who are veterans? What's the number of people who are families? What's the number of people who are struggling with drug addiction? And what's the number of people from that 1,000 who are aged out foster children? Okay, so let's say we got the following numbers. We got 200 for veterans, 300 for families, 100 for drug addicted, and let's say 400 for aged out foster children. And that all adds up to 1,000, right? So an equally valid function, right, could be to count the number of a certain item from the sample that you've collected. You could compute an average. You could compute the variance. You could compute all sorts of things. Anything that's a valid function over that sample data or those samples is a valid statistic, right? So a statistic is nothing more than a function calculated or computed over a sample. Nothing more, nothing less. Okay. So now the beautiful part about this is now you can use these statistics, these functions over your sample to estimate these parameters that govern the population. So what does this mean? So let's carry through this example. You have this thing called the population parameter, and this is introduction of more notation. Theta will be this Greek symbol that we use to talk about population parameter, right? And this other version of theta with the little hat on it, it's called theta hat. That's called the estimator, right, for theta. So here theta is a population parameter. If we say theta hat, that hat means whatever statistic or something you're reporting, that's an estimator for that parameter. So here's theta, here's the estimator for theta. So theta is the population parameter, theta hat is the estimator for the population parameter obtained from the sample. And the whole point of measuring statistics is that you're trying to find an estimator or something that's a good or reasonable replacement that you can use to stand in place for this population parameter that at the end of the day, you don't know. Does that make sense? Okay, so what does that mean? Given this example that we carry through, I say, I don't know ground truth, the actual detail of the homeless population in Dover. And again, I'm making these numbers up. So what do? I go out, dispatch some, caseworkers and some survey takers and stuff like that, and we're going to collectively find or sample 1,000 members of the homeless population, right? Okay, and we collect that data. We sit in a room somewhere. We crunch some numbers. We measure a statistic, the number that are in each of those categories, and then we're going to use these statistics to stand in place of these hidden parameters that we don't know. Right? Truly governing the population. So out of 1,000, if there are 200 veterans, that's 20%. So theta vet, we don't know, but theta hat vet is 0.2 or 20% probability, right? 300 over 1,000 is 0.3 or 30%. So then theta families is 0.3. For the drug addicted, it's 100 out of 1,000, so that's 0.1 or 10%. So we use theta hat addicted to stand in place of theta addicted, so that's 0.1. And likewise for foster, theta hat foster is 0.4. And so what we're doing now is we're saying, okay, well, I don't know ground truth what proportions are for the various of these 4 types representing the homeless population, but I compute a sample or take a sample, and I measure something over that sample. And if I've done this reasonably enough, and I'll explain in a few slides what reasonable means, or one definition of reasonable, if I've done this reasonably enough, then I can use this statistic, these hatted values, to stand in place of these unknown values. Does that make sense? So now I can say, in 2018, 20% of our homeless population were veterans. And then it's up to me, the person reporting the statistic, to tell you how I conducted that, how I calculated this, and also to do some error analysis. Does that make sense? All right, any questions about this? No? All right. So here we have estimators, our hatted values, for the parameters which are the unhatted values, and these parameters govern the proportions in this population of homeless, but we don't know what they are. We produced an estimate for them that stands in place, and we did this by taking a sample and computing a statistic, computing some function over this. Okay, so this is a diagram from the book, and it describes the relationship between the estimators and the ground truth parameters. So here you have some population. That's the individual collective set of units that are of interest. You do some data collection. This is your sampling. Now, sampling could be going out and surveying. Sampling could be, using some sensor. Sampling could be a whole host of things, looking through records of some sort, collecting web server logs, all sorts of things. The observation of data and collection of data is called sampling, right? So we have our sample, and that sample is indicative of the types of values for those measurements of interest that you're going to see from that population. So then you have your population governed by some parameters, but you don't know what those parameters are. You produce a sample or take a sample or measure a sample, and from that you compute some statistic, right? So when we talked about the mean, when we talked about the variance, when we talked about the covariance, when we talked about the correlation, those are statistics, whether you knew it or not. So we compute some statistic, and then we take the statistic and we use it to answer a question about the population, right? And so the focus of this semester is in this idea, bless you, of so-called inference. It's how you use these statistics that stand in place of the ground truth parameters to answer questions about the general population when you, at the end of the day, don't really know for sure what governs that population. You're using this statistic to stand in place. Now, there are mathematical tools that we'll cover that will measure the quality of your statistics, right? And if you do this the right way, you can pass those mathematical tests, as it were, the statistics will. You can guarantee with some assuredness that the statistic that you're using to replace the unknown parameter is sound, all right? And it's sound under certain conditions, and we'll certainly talk about those conditions. Does that make sense? So what can you do to make general statements about the population? You can do something called estimation, right? It's a data-educated guess, if you will. Hypothesis testing. What hypothesis testing is testing whether or not a value is typical of the population, right? If you've ever used these spam filters on Gmail or Yahoo, that's exactly doing hypothesis testing. It's collecting samples on what legitimate email is, and then it's building a model, computing a statistic, and then it's testing whether new emails are typical of legitimate emails. And if it's not, it says, this is spam. Now, of course, it makes mistakes. And when it makes a mistake, you correct it, and then it updates the sample with your correction, and it recalculates the statistics and performs that hypothesis testing over again. Modeling. Of course, we did a fair amount of modeling last semester, but there are other things we could do, etc. Okay? All right, any questions about this? All right, so this is in the book. So when you do this, of course, you want to make sure, or you need a method by which you can quantify, actually calculate how good your statistic is, right? And of course, this is called error, right? The difference between something that is perfect and something that's less than perfect, right? And so you can have discrepancies between the underlying population and the samples you collect, right? That is called error. And these errors can come from two major categories of areas. One is called sampling errors. Now, of course, when you select a sample, how you select those samples and where you apply those samples is going to impact how good your resulting statistic is. So if you're going to make an inference, try to draw a general conclusion about the population from this function you've calculated or statistic you've computed over the sample, the underlying method you use for sampling is going to impact the quality, right? And so a so-called sampling error is because you use a subset of the data, the sample can be off from the population, right? And so for most statistics or functions and methods you can use, the error will get smaller if you increase the sample size. And the reason for that is if you think about the homeless population, okay, well, if you're randomly selecting someone, you're not, for example, maybe you make the assumption that everyone wearing camo is a veteran, right? And if you said I'm going to select the folks wearing camo with the assumption that they're all veterans, is that true? Maybe, maybe not. But that's not completely random sampling, meaning you're not making any preference for one over the other. But in absence of good sampling method, as long as you increase the size of the sample, you're more likely to encounter different variations of that quantity of interest, right? And we'll talk about that throughout the course of the semester. So most sampling errors can be corrected by just increasing the sample size. Now, of course, from a practical standpoint, there are engineering limitations, right? Because if your sample is too large, you have to compute that statistic. And if you can't compute that statistic because there's too much data on your machine, you don't have the MIPS, so to speak, millions of instructions per second to go around, then you're not going to get an answer. So there's this trade-off. You want a good representation to correct for sampling errors, and that requires you to increase the sample size. But if you increase the sample size too much, you might not have the computational resources to calculate the statistic. So there's a trade-off. And how do you balance that trade-off? Then there are so-called non-sampling errors. And a non-sampling error deals with the approach that you took to sampling. So in the case of the homeless population that I mentioned before, if you only interviewed people who looked like they were, say, under 25, right? That's going to introduce non-sampling errors because there's a basic flaw in the methodology you use to go out and collect samples. So with a non-sampling error, it means your approach to sampling or your statistical method is inappropriate. And statistics cannot recover poor sampling, right? No amount of samples you take can recover you from choosing the wrong approach to sampling. You have to study how you do your sampling so that you can make sure that as you increase the size of the sample, the individuals that you collect data from, in the case of homeless population, are representative of the greater population. And how you do that is by not preferring one over another. How you do that is also by trying different locations where the homeless are known to congregate, okay? Because maybe those that hang out at the library are different from those that hang out at the park, so to speak, okay? All right, any questions about this? All right, make sense? Yeah? All right, so what are some examples, and these are just broad categories, of sampling errors that you can make, right? And these are structural sampling errors. The second case that we talked about, non-sampling errors, meaning the method of sampling was flawed. So the wrong population. And the example given for that is, say you survey 100 Samsung Galaxy users on campus about the new feature on the iPhone, right? That's just incorrect, right? Maybe dependent observations. You ask CS students if the bookstore has good prices, and I'll explain what the flaw is in each of these. Not equally likely, you sample randomly different flights. So you want to know something about the flying public, you go to different flights as people are coming off a plane, and you sample them, ask them questions. And let's say on each flight, you sample 10 of the passengers. And then there's also bias, meaning non-random preference. Phone poll about grocery items that are frequently purchased. Okay, so let's take a look at each of these. Now, of course, for the Samsung Galaxy, they have limited experience on the iPhone, right? Or maybe they prefer features in Android, so they're not really going to appreciate some new feature on the iPhone. So you wouldn't interview Galaxy users about a new feature on the iPhone. You'd want someone who has a certain level of experience with that particular platform, because that's going to be more representative of the population, right? So if you're going to make an app development choice, you wouldn't ask Galaxy users about iPhone, right? Because it's just you're gonna just get it wrong, and no amount of samples you can collect is going to fix that. Okay. Dependent observations. So students in the department talk to each other more frequently than students that are not in the same department, because you're in the same location, you're going to talk to one another. So they talk to each other more frequently, and they're going to influence one another's opinions. So in this particular example, you're not randomly selecting from the population of bookstore customers. So if you wanted to know from the students in general whether or not the bookstore has good prices, you might want to camp out near the bookstore and ask people on the way out, do you think they have good prices? Now, certainly, in the department, someone's going to say, hey, If you go on abebooks.com or go on amazon.com through the marketplace, you can get this, 15% cheaper. People are going to influence one another's decisions. Or even, I know nobody here does it. You find a mysterious PDF somewhere of the book, and it's free, right? I was a student. Well, they didn't have that when I was in when I was an undergrad, but I know it happens, but nobody does it here. So depending on observations, not equally likely. So on a flight, well, if you're going to randomly sample different flights, frequent flyers on a flight, whether the business travelers or other, they're more likely to be selected. And so if you do a random sample of passengers on flights, you're going to miss out on, say, the once a year family vacation travelers. So you're not going to get an opinion on air flight from those sort of customers. It's going to be overrepresented by folks who are frequent flyers. Right? Now, of course, the frequent flyer experience is a little bit different from the casual traveler or vacation traveler. Right? They get more perks. So they're going to, maybe they go into the lounge and have the buffet and they feel really good, and versus you do a little yoga to fit in the seat, and you're achy and all that stuff. But nonetheless, you're not adequately representing the profile of all the different members of the flying public. Now, the last one, suppose you only called landlines, right, for your phone poll about grocery items that are frequently purchased. Well, there's a relatively younger demographic, 18 through 25, for whom cell phone is their only phone, right? They don't have a landline home phone. All they use is a cell phone. So if you're going to only use landlines to do phone polls, calling, well, you're going to underrepresent those who are cell phone only users, who tend to be younger in age in the demographic. So whatever they purchase, you might decide, I'm going to run a promotion and develop some coupons or sales circular or stock up for something. You're going to miss the boat. Right? You're going to end up stocking up on something, putting it in the supermarket. No one's going to buy it because you underrepresented your population of buyers. Okay? All right. Any questions about this? And in each of these cases, and these are just for obvious examples, but the point I'm trying to illustrate here is that in each of these examples, no amount of increased sampling can help this, none whatsoever. Okay? So it's really, really important. That just begets the point that it's really, really important to think about how you're doing your sample design. And so in an assignment, the next assignment, you'll be doing a sample design, and I'd like for you to think about how you're posing your sample problem to get a suitable representation of a population under study. Okay? All right. Any questions about this? Does that make sense? Okay. So let's have an example. 10:34. We have about 10 more minutes. And so you draw examples from a population randomly, and these are examples are collected independently. And these two are very, very important, these 2 points. Independently and equally likely to be selected, right? This is really, really important to getting representative samples. Independently means that when you collect a sample, the value of the measurement that you get from that sample does not influence the next sample that you take. So for example, let's say you were doing a survey of students at Dell State. If you found a random person on campus and you said, what is your status, freshman, sophomore, junior, or senior? And let's say she said, I'm a senior. And then because she was a senior, you said, oh gosh, well, I really need more freshmen. Because that's a senior, the next person that I'm going to really contact, I'm going to make sure they're a freshman, right? That's the wrong approach. That's not independent. You're using the outcome of one sample to influence how you direct the next sample, right? So it's really important when you draw your samples to make sure that examples you collect are independent and therefore equally likely to be selected. You shouldn't have a preference for one versus another. Now, of course, for every rule, there's a counterexample, right? Sometimes you want to do so-called stratified sampling. And what stratified sampling says is that I want to take my population and I partition my population in a logical sense, or stratify, right? So let's say you have, there's like a freshman class meeting going on. You say, I'm going to go to the freshman class meeting and I'm going to get some, talk time at the meeting. and I'm going to say, hey, I'm doing this survey. I need 10 people. How about you, you, and you, you, and you, right? Then you go to the sophomore class meeting and you do the same thing. The junior class meeting and the senior class meeting do the same thing, right? That's called stratified sampling. Sometimes you want to partition or stratify your data and direct your samples within that subgroup. So while, yes, it's important that you collect your examples equally likely or independent, but there are cases where you specifically want to partition your population or representatives of your population. And then again, the samples must be representative of the underlying population. Now, certainly, if you're doing a survey about parking, you want to make sure you are representative of all the people that park on campus. And I know I'm salty about parking. There's faculty staff parking. There's student parking. For student parking, there are underclassmen and there are upperclassmen. There are graduate students and there are undergraduate students. There are residential students and there are commuter students. You want to have factors or things you divide your population into that are representative of the different types of usages of some resource if you're dealing with something like parking, right? And that requires sitting down, doing some research, and thinking about what you believe the structure of the population should be. Now, of course, when someone says, what was your sample design? You can always have the discussions about whether or not that was the right population design. And an example of the population design is that homeless population I mentioned. So I acknowledge the fact that these four categories are non-overlapping in my example, and that in the real world they might be overlapping. But that wasn't the goal that I was after for that example. So you can absolutely have the debates about whether or not your population that you designed or assumed is representative, but you still have to furnish how you performed your experiment, and part of that is the design of your population and the sampling approach. Okay. So let's take a look first. Any questions about this last goal for sampling? No? Does that make sense? Okay. So I think in the interest of not breaking apart two different submodules more than I should, let me just introduce this next part, and we'll end a little bit early because this is going to take some time to kind of build up. So I'll just introduce it and then finish it on the balance of Thursday, where we have a whole class period. So descriptive statistics. Now, descriptive statistics are a type of statistics. So a statistic, as I said before, is a function over data, any function. Doesn't matter what that function is, it is a valid statistic. And a descriptive statistic is used to describe some aspect of the population. So in this particular example, let's say we're going to sample the process time on a machine. Now, if you're familiar with Unixes, there's a command called top, and what top will show you is a list of all the processes that are running, and it'll show you what's called the CPU time as well as the wall clock time. Now, the wall clock time, as the name implies, is the amount of time that transpires from when you first run that process or program in execution up to this moment. The CPU time has to do with the fact that a process shares the processor with other processes on your system. And whether you know it or not, you have many dozens of processes running on your system or programs in execution. I can't assume you've had operating systems, so I always have to explain that. So what the CPU time is the amount of fractional time of each process gets some period of time on the processor and is kicked off to give a chance to another process to run, and then it goes back on the processor and runs a little bit and is kicked off again. And so the CPU time is the total amount of time that it's physically executing on the CPU. And so let me bring up my terminal and show you an example of what top will show you. So let me come down here, clear, top. And when I run top here, you'll notice there are a bunch of columns. That first column on the left is labeled as PID or process ID. And there's the command. That's the actual command that was run in order to do it. Now, some of these commands I've run myself. Other of these commands were started by the operating system, so they're services. And so it gives me the percentage of the CPU, the fractional percentage of the processor that this process has used. And for example, air server is something I'm running to do mirroring from my tablet to my laptop, which doesn't always work well. And then here I have the amount of time. I believe this is CPU time. I'd have to look it up to make sure. And you'll notice here that I think it's CPU time, yeah, because some of them are incrementing and others are not. If it were wall clock time, they'd all be incrementing. So this is CPU time. And so you'll notice some processes are getting the CPU and some are not getting the CPU. Some might just be idle waiting for asynchronous events. And so this is what top does. And in this example, we have the amount of processor time for various processes executing on a system. And so let's define n to be 30, and 30 is the number of jobs or programs that you run that are executing on the CPU. And the quantity being measured is the amount of CPU time that each of these 30 randomly selected jobs have run on the CPU through something like top. Right? And so here we have 3 rows of 10, 70 up here is the first one, and 19 is the last one, right? So let's say you have this data, and now, assuming these values come from some distribution of runtimes, now this is going to be a gamma distribution, right? It's a multi-phase execution, if you were curious. So assuming these values come from some distribution, we can measure a lot of things about this, right, that you might be interested in, so-called descriptive statistics. You have the mean, which we learned from last semester is the center of the distribution. We have the median, which we'll learn more about this semester in data analytics, which is the central value. Now, the median and the mean are different, and we learned last semester you can use the relationship between the median and the mean to talk about the skewness of a distribution. The quantiles are values that cut the distribution into equal parts, and those parts are based on area under the curve. And the quartiles are the 25% cut points. So when you talk about quartiles, they're the values such that if you cut the distribution, slice it up at those values, you have a total of 25% of the probability in each one of these resulting pieces. The variance we talked about is the dispersion about the mean. The standard deviation, which we talked about last semester, is the distance about the mean in context. And the purpose for the standard deviation was because the variance has a problem because it's squared. And when you square something, it's hard to say degrees Fahrenheit squared, right? And when you make a comparison between distributions to talk about their dispersion, it's kind of nice if the dispersion is using the same units as the center, as the mean, right? So you get the standard deviation by taking the square root of the variance. So we also have things like the interquartile range. And the interquartile range is just the numerical spread between the quartiles. It's another way of measuring dispersion, and we'll talk about these in the next couple of slides. And so it is 10:43. We'll stop there, and I will see you all on Thursday. I look forward to your assignment submissions.